Welcome to today's webinar organized by the Spatial Analysis and Simulation Lab community. This lab is dedicated to advancing the understanding and practice of architecture and urban system. Our vision is to transform cities in Egypt, Africa, and the Arab world into healthier, more sustainable, and resilient urban environments through innovative simulation, AI, and digital solutions related to spatial analysis, Internet of Things, big data, and data-driven insights. Let me introduce our guest presenter today, and actually I would like to thank him very much for accepting being with us. I'm going to introduce Paul Waddell, the CEO and founder of UrbanSim. It's my pleasure to introduce our esteemed presenter for today's webinar, as he is a globally recognized thought leader and a serial entrepreneur specialized in urban analytics, urban data science, decision support systems, and urban simulation. Paul Waddell is the CEO and founder of UrbanSim, which offers advanced solutions to improve public and private decision-making, to accelerate housing supply, improving affordability, reducing greenhouse gas emissions, enhancing climate resilience, and promoting equitable urban quality of life. UrbanSim helps stakeholders indicate future outcomes and design smarter urban interventions. It's a model are used worldwide, influencing planners for over 80 million people across 5 continents. Before founding UrbanSim, Paul Waddell created Synthesy, a startup focused on urban simulation that was acquired by Autodesk in 2015. He also has distinguished academic background, having served as a professor and chair of the Department of City and Regional Planning at the University of California, Berkeley. As a senior fellow at the Berkeley Institute for Data Science. His pioneering work in urban micro-simulation, particularly the development of UrbanSim, has earned over more than 10,000, I've checked today, there are 11,000 something citations, and several National Science Foundation grants. Paul holds a PhD in political economy from the University of Texas, Dallas, and a master's degree in human ecology from the University of Texas School of Public Health. Paul's career has focused on understanding metropolitan regions as a complex spatial political economies. He advocates for collaborative, multidisciplinary approach to tackle urban development challenges in an era of global interdependencies and environmental awareness, aiming to inform sustainability and democratic infrastructure choices. In summary, Paul Waddell is a distinguished leader whose innovative work and UrbanSim transforms urban planning. His commitment to using data and simulation to create smarter, more resilient cities has a global impact, and we are honored to have him today sharing his expertise. Please join me in welcoming Paul Waddell. Paul, the floor is yours.
All right, thank you very much for that very nice introduction. I'm delighted to be here. I know you asked me to send a short biography, and I failed to do so, and instead you did a much better job than I would have done. Thank you so much. I am honored to be here with you all. I do welcome interruptions along the way. All right. I've been doing urban modeling and urban simulation for quite a long time, as I think you would have perceived from Nabil's very nice introduction. So I'm going to take you on a bit of a journey along the way that I have traversed in my intellectual journey and research journey, beginning with this slide, which I put together. It's been 15 years now, so you can see it ends at 2010. But I think the basic outlines here, the long-term history of urban modeling from the 1960s roughly, is maybe useful for some of you that know parts of this spectrum and perhaps not all of it. So I'll mostly leave this for reference, but I'll just say a couple of things about the earlier generation of models. They tended to be very abstract. We might think of them as big theory, little data, well before the era of big data and machine learning and artificial intelligence. The gravity models were essentially literally a translation of the law of physics, the gravity law, into a representation of trip distribution and the like. Very little behavioral content in it. And amazingly, it was used for practical planning applications for a number of years. I would say not terribly successfully, but it was used extensively. It's still used in trip distribution models, in transport modeling, surprisingly, but it's still getting significant use. There's another train of thought and modeling that follows input-output modeling and the spatialization of that. Very computationally intensive and essentially trying to adapt the idea of international trade modeling to intra-urban zones, which I always found a little bit wrong-headed. It just didn't seem like the right theoretical framework to think about cities, in my view. And then there's the whole field of urban economics, Alonso, Mills, and Muth, the monocentric model, which was quite impactful in terms of theory. In terms of practical modeling applications, the monocentricity aspect, of course, was something that was quickly debated and argued about as cities became more polycentric. But the basic ideas of accessibility being central to understanding land prices, property prices, and rents has had a lot of staying power and influence over the years. That was followed by rapid advances, Nobel Prize in economics by Daniel McFadden for development of random utility theory and the discrete choice models that emerged from that. And then a final thread that I'll mention is microsimulation. This had its early start in around the mid-60s, Guy Orcutt, and it was used for evaluating tax policies and taking a large sample of population, individuals, households, and calculating the tax impacts of changes in tax policy. Several of these ideas helped inform the development of the work that I did. No work occurs in a vacuum. I certainly did not invent everything that I have done over the years. I built on very strong foundations and hopefully did a little bit of innovation along the way. My roots academically, intellectually, really were environmental, ecological. I was interested in the interplay between urban development and ecological dimensions, resource use, pollution, conversion of land from natural uses or agricultural uses into urbanization, and these dynamics between the natural ecosystems that we inhabit and the urban systems that we create. And I had a wonderful and long collaboration with the Urban Ecology Lab at the University of Washington, where I was a faculty member before joining the Berkeley faculty. And this paper was published with Marina Alberti in 2000, but it captures the ideas that we were trying to pursue. And we did get some NSF grants, National Science Foundation grants, to flesh these ideas out and implement many of them in research models of the time, working with hydrologists, foresters, ecologists of different types. It was quite a fascinating multidisciplinary perspective. And I really think that the biggest problems we have require this kind of interdisciplinary focus. I began coalescing the work around urban modeling when I wrote this paper and published it in 2002 in the Journal of the American Planning Association. It's been cited pretty widely over the years and still gets a good number of citations every year. But it was really our first iteration of implementing urban simulation models, and they have evolved a lot over the years since then, as we've learned both through research and then through application. Some of the intellectual roots are again represented here. The ideas of representing individual agents. You can think of this as agent-based modeling, but that term tends to get a little bit overloaded. There are certainly, there's a whole field of agent-based modeling that is very bottom-up, very theory-driven, not so interested in empirical calibration or validation, but in exploring emergent behaviors from embedding agents with some simple behaviors. That is not the realm that I have pursued. I wanted to do something that was agent level, but that had a stronger foundation in data, and being able to estimate the parameters of models or calibrate those parameters and make sure that they fit data well. So a more data-driven approach. And I think microsimulation perhaps describes it better than agent-based modeling, just because of the confusion around what agent-based modeling is. But again, representing households and their choices. Some of them, like aging, we don't get to make a choice about, it just happens to us. But most of the other choices represented in that left column, we make, and we make them in a particular context, and we make trade-offs as we're making those choices between, say, housing costs and accessibility, access to amenities, and so forth. So this behavioral framework is something that is very consistently theme of the work that I've done in urban simulation. Besides these general frameworks, we had to also, I think, begin to understand how real estate markets and real estate development decisions work, and how outcomes such as housing prices and housing affordability more recently come to be. And in particular, we're interested in, as urban planners and urban policy makers or analysts, interested in understanding the roles that governments play in where they provide infrastructure, how they regulate the use of land, how they regulate the operation of real estate markets. Keeping in mind that real estate markets do not exist in a free market sense. They exist always in a regulated sense. Land and its ownership is regulated, transactions on land are regulated, use of land is regulated to varying degrees. Infrastructure provides the basic usefulness of the land for development and so forth. So urban development happens and real estate markets happen only in markets as they are framed by governmental actions. And so with that basic thinking, we developed over the years a set of individual models that coalesce into a model system representing demand for residential real estate, demand for non-residential real estate from businesses, and the supply of those through real estate development decisions. And all of these being driven by macro demographic and economic forces that influence the particular context that you might be looking at. And as a planner, I have looked at a lot of different local contexts across the United States, Canada, Australia. I've worked with collaborators, as I'll mention in just a moment, in South Africa, research in Asia, Europe, etc. And across these contexts, there are some broad themes that kept reemerging in different degrees in different places. And it's certainly not an exhaustive list, but these are some of the core driving questions that have motivated the development and use of UrbanSim in many places. The first one is understanding and being able to plan for infrastructure, urban infrastructure. Of course, that is transportation is probably the most prominent one in many places, but water and sewer infrastructure are critically important as well, energy infrastructure, and so forth. And so for long-term planning of infrastructure, it typically requires 30 years or sometimes longer to plan for the implementation of the development and implementation of critical infrastructure. There's a need to understand how urban dynamics are changing, where will there be growth what type of growth, and how will that shape demand for infrastructure. But then what I found when I started doing actual applied planning work was that infrastructure planners often thought their job was to respond to demand and to think of it as a one-way influence, that demand would happen sort of independently and it would shape the demand for infrastructure, and therefore you could simply have a response by putting infrastructure where it was needed. Unfortunately, it's not that simple. And there's been a long-running debate that I think is now largely settled, that transportation infrastructure, for example, and you could say the same for water and sewer, when you provide that infrastructure, it shapes demand for it. In other words, if you build roadway systems, if you build water and sewer systems that extend into previously unserviced areas, it creates opportunities for development. So it shapes development. It doesn't just respond to development pressure. And so when I started doing this urban modeling work, that was not widely practiced or acknowledged, especially in transportation planning. And it has taken years to finally break through that understanding and have it become more mainstream in its adoption. And then more quickly, the last 2 points on here, how will infrastructure and land use regulations shape real estate markets? And I recognize that there's wide variation in the degree to which development regulations even matter. There are many places where informal settlements are occurring. Obviously, that's true in many parts of Africa and the Middle East, to perhaps a somewhat lesser extent. True in Latin America. It's certainly true in many of the places that we've collaborated and done research. Even in the United States, there's highly differentiated use of regulations and how impactful and binding they are. There are places where if developer wants to change the zoning, they can simply ask for a variance and they will get it. In other places, it's very constrained by policy and it's very hard to change it. So there's a lot of variability in that, but it's still important to understand. And then finally, we're, I think, all experiencing varying degrees of impacts from climate change and having to grapple increasingly with resilience, whether it's droughts or floods or storm events, extreme heat events. All of these are increasingly impacting urban settlements. And of course, urban settlements are increasingly contributing and have contributed to greenhouse gas emissions and global climate change. So more and more local governments and state and national governments are trying to grapple with this, in part through how they understand the emissions being created by transport and by buildings and by industry. So UrbanSim has gone from being a research exercise and source of research grants and various research exercises to being a widely adopted tool for metropolitan planning and city planning. This is mostly true in North America, also true in Australia. We're starting to work in New Zealand as well. But there have been research applications of this, as I've mentioned before, throughout the world. And I mentioned one earlier. We've had a collaboration with the Council for Scientific and Industrial Research, CSIR, in South Africa for many years. And I've visited South Africa and CSIR through that collaboration and tried to support their work as best we could. And I really appreciate the network that you have put together here and the one that I'm speaking to right now. I think this is a fantastic initiative that you're taking, and anything I can do to help facilitate access to technology and innovation, I would be happy to do what I can within the limited resources that I have. So I have two different parts to a presentation and probably way more material than is appropriate So I may not present all of it in this talk because I would like to leave some time for discussion. But this next segment of the talk gets a bit technical, but given the scope of topics that this network has expressed interest in, I think you'll find it interesting. And I'm going to talk about challenges in developing models like this and how recent innovations in artificial intelligence and machine learning have enabled us to make some breakthroughs to make this model development effort much easier and much more data-driven. So I'll start by just an assessment of the problems. As I've mentioned already, been developing models now for over 25 years. Over that period of time, it has gotten somewhat easier, but even very recently, I would say it still took much too much effort to develop a model that was actually useful for planning purposes and for operational use in supporting decisions, whether they be transportation planning or land use planning or water and sewer or other applications. And once developed, the models generally are complicated to run. They take a long time. If you're using local computing resources, they can overwhelm those resources. And all of this, I think, has led to a degree of skepticism that urban models, urban simulation is not for everyone. It's too hard. It takes too long. And therefore, it's, I think, undermined itself to some extent and slowed its own advances just by the difficulties, the challenges that are involved. And I should mention that there is a research paper that was published in 1973 by Douglas Lee, Requiem for Large-Scale Urban Models, and he did a sequel to that in 1994. These are probably a good read even now. I think any of you that are interested in urban modeling, it would pay to read these earlier papers that were really harsh critiques of urban modeling. The first one would have been responding to that top row of models in my earlier chart, ones developed in the 1960s that were largely aggregate, cross-sectional, equilibrium-based models, very abstract, not very behavioral. And it actually slowed down the innovation of urban modeling for quite a few years, as there was we went from a hype syndrome like there is right now around AI to a valley of despair that follows the hype cycle. And it took a long time to regain traction and innovation. But it has been accelerating. And I put this slide together mainly to communicate a single point, which is that it used to take us multiple years to get an actual operational model up and running, properly calibrated, and useful enough to be put to actual work in planning. But over the last several years, and then I'll transition to talking about what we've done in the last 2 years, we significantly accelerated that process. We've made it a lot easier, a lot quicker to build useful models. And I think the key word is useful, and useful for particular purposes. I think no model can exist in a vacuum outside of the applications for which it is intended. That is, you need to start by asking, what are the questions we need to answer? At what level of granularity? And then work backwards to a model design to make sure that it fits that. So this really encapsulates some of what I've already said on the previous slide and discussing it. We have invested a lot in automation of data pipeline processes. There's still, I think, a tremendously large amount of game to find in further automating and refining that. And I do think that AI and machine learning processes will help. We've focused more on acquisition and pre-processing of large-scale data sets just to get some economy of scale. We've invested a lot in modular software engineering. And this is a topic we could digress on later in the discussion. I think it was a particular challenge when all of our work was fully open source, and it was very hard to maintain coherence and further evolve it. But nonetheless, software engineering practices are getting better. We're getting smarter about how to make software modular and easier to maintain, and using templates and components for models and variables to make them increasingly reusable. So we made a lot of progress from, say, 2016 to 2021 over a 5-year period. And I think we had gotten to the point that the data development process was less the bottleneck. Calibration became the biggest bottleneck. And I refer to calibration here as ensuring that all the equations in a model system, when put together and applied over a period of time, make predictions that are reasonable and can be compared to the real world that we observe, and produce sensible and reasonable results. Ideally, if we can do that over a historical period that we can observe, that it can reasonably well represent and recreate that historical period. I refer to this as the dark side of modeling because if you look at the published literature, you see a whole lot about very careful econometric estimation of models and biases in the estimation of certain parameters and violation of assumptions and so forth and so on. But you see very little about the practical aspects of calibrating a model system, especially over time. And I think modelers don't like to talk about it very much because it's really hard to do, and it's something that we really have not, as a field or as a collection of fields, really mastered. I think a lot of the traditional calibration techniques, they're quite manual, they're very time-consuming, they often involve adding spatial constants. And when you're using cross-sectional data to calibrate the model, like you do in, say, a trip distribution model, or any other component of a transportation model for that matter, you typically are using things like traffic counts to calibrate at one point in time. And so you're having the model try to reproduce the current state. And when you do that by adding constants, those constants absorb the errors. And they may produce a calibrated result that looks like it reproduces the current state well, but it may not explain much at all because so much behavior has been sucked into the constants. And so that has a problem of reducing model sensitivity, which is really why we build models in the first place. We want to do counterfactual analysis to change transportation plans, water and sewer infrastructure plans, land use regulations, make other investments, possibly financial policies. And we want to test how urban dynamics will change as a result of those interventions. And if you've reduced model sensitivity through poor calibration techniques, the model is no longer useful. It's insensitive to those things. I think this is a really key point for modelers and should get more attention. So the work that I'll describe in the next segment here is motivated around and by solving that problem. And it emerges from studying what's going on in the explosion of artificial intelligence models that have for years demonstrated their ability to make better predictions, more accurate predictions than classical statistical methods have been able to do. And we've done some of our own comparison of AI models to statistical models and find them to be extremely capable of handling things like spatial autocorrelation, nonlinearity, various things that statistical models really struggle with. On the other hand, they tend to be very black box. I could generate for you a wonderfully predicting neural network model of urban development, but it'll be a black box. And I can't use it successfully or as successfully for policy analysis and planning because it's unclear whether it will support that kind of counterfactual analysis under different conditions because we don't understand what it's doing internally well enough. So this answer may change over the coming years as explainable AI continues to make advances. And I think the world of AI and the world of more behavioral modeling will converge increasingly. But we've taken a particular pathway to try to generate some convergence. And that's what I'm going to discuss in the next short while. So our objective here is to try to leverage some of the advances in AI to produce models that predict longitudinally in a more accurate way, and to streamline and facilitate the calibration process, but at the same time try to preserve the explainability and the utility for counterfactual policy analysis and planning. So that's the challenge, how to get the best of both worlds, the best of behavioral modeling and policy-based counterfactual analysis with the best of AI. Not a trivial thing to do, I will say. So to rephrase the question, how do we take UrbanSim, which is a small area model of urban growth, which we typically in the past have estimated off of cross-sectional data, to approximate a longitudinally observed data stream or dynamic? And can we do it without losing the behavioral sensitivity? So what does that look like? So I'm just going to make a few references here to how commonly we're encountering machine learning and AI models today. I mean, obviously, what was it, maybe a year to 18 months ago, ChatGPT came onto the stage in a big way. And almost overnight, everyone seems to be using ChatGPT for all kinds of things. It really created a public awareness of how fast and far AI has emerged and have become, much more useful for day-to-day tasks. So some examples here: Uber Eats to power recommendations, PinSage for web scale recommender systems. Whenever you're using Google Maps and you're doing routing, it's doing routing based on graph neural nets. These are becoming part of our day-to-day infrastructure for information technology. So how are these models trained? I'm going to focus on recurrent neural networks because they have a particular affinity and similarity to what we're doing in urban models, especially dynamic urban models like UrbanSim that simulate from one year to the next year to the next year. So you can think of these recurrent neural networks as a sequence that is repeated, a neural network that's recurrent, time step by time step by time step. And there's, I think, a pretty natural mapping between thinking of a recurrent neural network as an unfolded graph and thinking of an urban simulation as an unfolded graph. We're modeling from, say, 2016 to 17 to 18, all the way out to perhaps 2050 into the future. And within each of those years, you can think of it as a graph of equations that are adapting and updating the state of variables. So what is the key element to training these recurrent neural networks? It's backpropagation. This graph shows it a bit abstractly, but the basic idea is that it's working backwards through the calculations, calculating exact gradients to update the parameters that feed forward through the model based on some loss function that's being minimized. This is another description of it. Again, just thinking of it as working backwards through all the partial derivatives of every element of the model system to go back to the beginning and update the initial weights or parameters for the model system. So it requires some basic things to be able to do this. It requires automatic differentiation. It enables computation of exact gradients, which are the partial derivatives of the loss function with respect to each weight or each parameter. And it's doing this jointly for all of the parameters in the model system. So this process can efficiently update the weights or parameters using exact gradients in a way that previous technologies for calibration just could not. We've used a variety of different calibration techniques, and at most they can handle a modest number of parameters and not very efficiently at that. So the efficiency of using exact gradients is really an incredibly important breakthrough for us, we think. So again, reframing the question a little bit, instead of asking, or to phrase it in a different way, rather than asking which parameter values were most likely to generate a cross-sectional data set, we're instead asking which parameter values were most likely to generate a longitudinal dynamic. So we're actually calibrating the model over time. What we've done with UrbanSim in the last 2 years is create a fully differentiable implementation. We've had to recode it from scratch to make every single step of the model system fully differentiable. And you can think of it again, translating it graphically like this. It has a set of parameters. You run that model forward in time. It generates a sequence of urban data. You compare the sequence of urban data that it creates to what was actually observed, calculate a loss function from that, and do backwards inference through the backpropagation. So it's a differentiable program. It's optimizing urban models using automatic differentiation. It's calculating gradients in the simulator, and it's learning parameters from longitudinal data. So that's the basic mathematics and idea behind it. And again, this graph is another way to represent the idea. It's an urban model system predicting spatial dynamics. There's a set of observed spatial dynamics over the same period of time. We compare those to compute a loss function, which generates a score. And then we're doing optimization through the exact gradient calculation to update the weights. And we might do 2,000 iterations of a 10-year simulation to calibrate the model, but we're now able to do that in generally 30 to 40 minutes. So it's using a whole new software implementation that we've created called differential UrbanSim, auto differentiation, and then it can compile these into CPU, GPU, or TPU, different accelerators for parallel processing that are now broadly available on the cloud. So some of the things that this allows us to do are multi-geographic level optimization. So it might be different levels of political geographies that we're looking at, plus census geographies. It allows us to jointly optimize all the model equations together over multiple years. That allows us to handle the linkages between the models better than we've ever been able to do. It allows us to restrict the signs on particular parameters, like price coefficients should be negative in general. It allows us to do some things like regularization, which is typical in machine learning and AI. It allows us to get more creative with loss functions to build in the desirable properties of the simulation directly into the loss function that's being used to train the model. And potentially, we think it has a lot of application to multi-region learning, to be able to take multiple regions and learn the parameters jointly, plus transferring that learning from one place to another. So how well does it work? We've been doing this in multiple places now over the last year or so, and over a 10-year simulation, the correlation at the end of the 10 years at a slightly aggregated level of geography is incredibly high for households, for housing units, and for employment. Now, that is a somewhat easier test than this one, which is comparing, these are additional endpoint correlations for prices and rents. So we're now not only able to more accurately capture quantities of households, housing units, employment, but also market factors like prices and rents. That's a really important advance over what we've previously been able to accomplish. A second level of testing and validation that we're now doing is comparing the changes over time that we are simulating compared to the changes that we can predict. This is a much harder test because a lot of what you observe maybe in 2020 was already present in 2010 when you start a 10-year calibration process. So predicting the changes more accurately is really what we're ultimately trying to do, and this is a better test of that. But you can see this is still producing very high correlations on the changes, even on prices and rents, although rents are a little bit messier than prices. So we think this is making some important advances in our ability to quickly calibrate and capture longitudinal dynamics. And perhaps that has some bearing on the potential to apply these models in places where the data might be a little bit more messy, or in some cases less available, but that need to be able to stand up models like this and use them. Some other things that we've learned are kind of positive side effects of using this approach are that we're able to do things now like equilibrate supply, or rather demand, for real estate, like how many households want to locate in different parts of the region, with prices and rents. When there's excess demand for a location, a lot of people want to go to a location. That competition tends to drive up prices. But unless you have some dynamic embedded in the model that reflects that, it's very hard to capture. And so this equilibration is an important part of that aspect. So as I mentioned already, typically we calibrate using 1,000 to 2,000 iterations of a 10-year simulation. Even for relatively large regions, that tends to complete within 40 minutes or so. And then large regions like Chicago, we can now run a full simulation of 30 years or longer within a relatively short amount of time. We're getting most regions down to about a 10 to 20 minute simulation time for a 30-year simulation. And we're not even fully taking advantage of GPU technology yet. So as we look at compiling to GPU for simulation, we think that could increase by another order of magnitude. The other thing that we're gaining confidence with this new approach for better handling is enabling us to better tease out areas that are growing, areas that are stable, and areas that are declining, because they often coexist in the same region, the same metropolitan area. It may be a rural decline and an urban growth, or it may be different parts of the urban and metropolitan region that are experiencing potentially rapid decline in one area and rapid growth in another. So we're now starting to capture that dynamic better. I'll just briefly mention this, that sometimes we don't have the data we really want, but as modelers and as researchers, we can hypothesize an equation. I give an example of housing demolition, for which we don't really have good data, but we're able to construct the model and initialize the parameters for it. And in the context of all the other equations in the model, we're able to calibrate a demolition model along with the rest. We're still in the early stages of this, and I'm sure it has limitations that we're just discovering and have not yet fully resolved. But like with most machine learning and AI training models, we're able to leverage techniques and computational libraries that help us to trace the gradients and trace the convergence of model parameters as they're stabilizing through the course of the calibration process. The other area that we're working on using the same differentiable modeling and the same kind of loss function minimization technology, but in the geometry space, and I should say the architecture space as well, is beginning to optimize building massing while respecting building typologies, like you see a podium tower instance here. This is going through a generative algorithm that is applying some of the same techniques we've been applying to the modeling more broadly, but down to the site scale. So it can account for the geometry of the site, the geometry of, say, zoning constraints like setbacks and height restrictions, building typology restrictions, and so forth. And we're quite excited about the potential to further develop this into an independent type of application. So I'm going to close this section of the talk and perhaps the whole talk, depending on time and interest, with just a few comments about what's next for this particular area that I've been discussing, this differentiable approach to modeling. We want to be able to have 2 time periods to do proper machine learning training techniques, have one that's a calibration period, followed by another one that we don't use in the calibration at all. We simply simulate forward and observe how the predictions compare to the observed changes over that holdout period. Unfortunately, every time period is unique, and the most recent time period includes the COVID pandemic. So there are challenges in doing this, as you might imagine. We're also working to integrate additional target data and loss function components, because that turns out to be, I think, one of the most creative ways to be able to refine and improve models to address different types of planning questions. We're going to continue expanding the applications of the models more quickly and use them in a more pooled way for multi-region simultaneous model training as best we can, and begin to extend the framework that we've implemented more into travel modeling as well. And then my last slide on this series is that we will be releasing a new version of the model platform on our cloud platform, hopefully to enable modelers anywhere, including perhaps in this network, to just be able to use a web browser to build models for your local regions and deploy them and support them. We do want to support collaboration with the research community like this to be able to test alternative model specifications, different models, potentially using a shared test bed. Depends on data availability and restrictions on data. We're also going to continue working on a rigorous and longitudinally comprehensive model performance benchmark suite, both emphasizing accuracy and sensitivity because they're both critically important. And I make a reference here to something that probably most of you would not have heard of, but I tried to create a consortium of researchers back in, it was around 2005, working with Eric Miller in Toronto and researchers in Europe and elsewhere, to try to have an open source platform to collaborate. And unfortunately, it didn't really happen, even though we had created the open source platform and invited people to collaborate. It never really materialized. But I think, perhaps there's a new opportunity with a cloud platform now to try to facilitate something like that and gain as much collaborative learning as possible. So with that, I want to take a pause here. We are close to an hour in, and maybe I'm going to stop sharing for just a moment and see if there are questions, if there are topics that people would like to discuss. What I have on reserve, if there aren't many questions, is a set of slides to go through what the platform actually looks like at this point, some embedded video and so forth to show what it looks like. But I've been talking now for close to an hour, and I think in the interest of not boring everyone or having you fall asleep, maybe I'll pause, see if there are questions, and if we have a lively discussion, then we can save the other for another time, perhaps.
Well, actually, we want both the questions and the follow-up.
So it's entirely up to you. This is your session, and I'm happy to go back into presentation mode. I can probably do the rest in about 10 to 15 minutes.
If you wish, we can
If
continue.
that's
Yes. Yeah, that's
if
perfect.
that's what you'd like to do, we'll do that.
Yeah,
then.
because
All
I
right.
think people would like to see insights how this
Okay.
simulation model is operating.
What it looks like.
Yeah.
All right then. I gave you a chance.
No, we're going to have questions. No worries. But
All right. So what I'll do in this last part then is go through what the cloud platform looks like that we've built over the last couple of years. And I'll start out by just describing it as a decision support software as a service platform. The goal is to have a lot of predictive analytics that you can then manipulate by doing experiments using the user interface to generate a variety of outputs and visualizations. So it is a cloud platform. It uses a modern browser interface. We've mostly tested it with Chrome, Safari, Microsoft Edge to some extent, but it should work with most modern versions of browsers. One of the elements it contains is Google's photorealistic 3D tiles. This is really just for context. It's a static mesh. It looks good. There's a little bit of lagginess to it, but for especially meetings where you're dealing with non-technical people, you're dealing with policymakers perhaps, or even community residents, it's helpful to have something that's visually recognizable. And especially when you're talking about topics like density, being able to see the third dimension in your work, in your local region, and be able to talk about things in less abstract ways than floor area ratios or height limits on buildings. It certainly can be helpful to have this kind of capacity. But the first thing that planners typically want to do when they're wanting to prepare a plan, develop a plan for an area, is understand current conditions. And so what we've done with the cloud platform is populate it, first of all, with a lot of existing data from the census, from other data sources, and make that thematically available. So it's easy for someone that may not be a GIS expert to quickly access the data, search it thematically, load it, look at some metadata about it, and even style it using basic tools that would be familiar to anyone who has used GIS very much at all, but hopefully easy enough to navigate that even if you're not a GIS expert, you can quickly learn how to style something and exclude zero data values, etc. And we'll continue refining this, but the goal is to make it as simple to use as possible. What we're doing here is creating a snapshot. It's not a screenshot, not a static image. It's a dynamic map focused on that particular data styling, that layer and that styling. And it can be shared. You can copy a link and share it with other individual people at a particular email address, or you can make it public and share it with anyone, not specifically an individual. So this kind of data exploration, exploring current conditions, exploring the styling of the data to tell a story, to convey a message, and then be able to create these bookmarked views of the data, either to help you just go back to different views if you want to be able to tell a story, perhaps for a presentation. You can create a storybook essentially. And of course, you can do some of these sorts of things with ArcGIS if you're an expert and you have a license and so forth. But the goal here is to try to make this more broadly accessible. Now let's turn to urban planning. And I realize, again, this is a little bit of a US-centric part of the presentation, San Francisco, a very iconic city, very built up, very expensive, I might add, is going through a bit of a challenge to create enough new housing to take some pressure off of housing affordability that is at crisis levels. And so we're working with the city to enable them to, first of all, visualize and analyze their current zoning, and also to begin exploring alternative zoning plans. So you'll see loaded up in just a second here, current version of an alternative zoning plan that is being considered. You see some transit-oriented development sites like this one. You see some corridors out to the somewhat to the west of the central business district, where there's an attempt to have gentle upzoning, and in some cases a little bit more concentrated upzoning, to try to begin opening up corridors that are well served by transit and enable that to be communicated to people through these, not only the color coding for the zoning, but also the extruded 3D envelopes of zoning. But that's still not very analytical. It doesn't really help us understand much except for a visual framework, roughly the heights implied by these different zoning types and locations. What we've also started doing is creating a set of independent calculators or toolkits for analyzing zoning in more detail. So what just ran here for the whole city of San Francisco is a capacity calculator. And it went through every single parcel in the city and computed its capacity based on all the zoning detail available to it, and exclusions where parcels would be maybe exempted or not used for the calculation. And it's representing this back to us as users in both a parcel level of detail and an aggregated level of detail, which gives a quick overview of the spatial patterns. And now this is doing the same calculation for the alternative zoning. Takes a little, around 10 seconds for this calculation to work. And once it does, it creates these new data layers that you'll see on the left, the total capacity. And again, it shows it here at the census block level. And I know you can't directly remember probably exactly what the pattern looked like with the previous zoning, but it does show significant increase in capacity. And you can drill down to the parcel level to study that in more detail and zoom into the areas that might be contributing to those block level patterns. So this is helping the city internally develop their revised zoning plan, and also to be able to communicate about it to their stakeholders. It is a very contentious process. San Francisco is quite political, and zoning changes like this are generally very difficult to get done. The next stage in the application is financial feasibility analysis for the development. And so this uses a financial model called a pro forma. It's the kind of technique that's used by developers to evaluate whether they should go forward with a project. Will it be profitable enough to build? And so it does a lot of financial calculations around the cost of the development, cost of acquiring the existing site, the cost of the construction, cost of the financing. And in the case of cities like San Francisco, which have policies like inclusionary zoning that require a developer in some neighborhoods to include a certain fraction of their housing units at a level that's below market rent. So perhaps where households that are at 80% of the area median income could afford it at only 30% of their total income being spent on rent, which is the definition of affordability broadly used in the US. So this does that calculation, much like the capacity calculation, but it's now calculating the profitability of development and how many units achieve a certain threshold of profitability that would be typically considered as viable in the market. And then I've already talked a little bit about this generative algorithm, so I won't say more about that. We are trying to expand it to a slightly bigger scale so that it can be used for, say, transit-oriented development or corridor development planning. It's still very much a work in progress at this point. But one thing that we have been experimenting with is multi-objective optimization for this algorithm. So one dimension of optimization could be the massing, maximizing the square footage of the building, subject to the constraints of the site and the zoning. Another dimension could be profitability or return on investment. Or if it's an affordable housing project, it might be trying to minimize the cost per unit or the subsidy required to build that complex. And increasingly, we could imagine embedding multiple dimensions. It could be daylight access and energy consumption. It could be various other things, provided that we can add those components to the calculations. Another area that our users commonly ask us to provide some support is tracking developments that are in progress, a development pipeline. And so we made it easy for them to add and track and monitor developments in progress, and to be able to add them to an inventory. In the interest of time, I'm going to keep going a little bit more quickly. We're working a lot with regional planning organizations and cities that are trying to better coordinate their transportation investments and their land use policies. And that's easiest to understand around transit-oriented investments and transit-oriented development. So we have added some tools to be able to add new transit stations and lines. This happens to be a bus rapid transit network in El Paso, Texas. And we're working with them to help them find ways to organize their urban densification patterns to reduce emissions and improve their air quality substantially. Also by removing vehicle miles traveled and greenhouse gas emissions from their environment. A key part of that is understanding accessibility patterns. So we've also created an accessibility analyst that allows using multiple modes of transportation: driving, walking, biking, walk plus transit, which is what you see on these particular slides. Here we're looking at a bus rapid transit system and access to retail opportunities within 15 minutes on the left and 30 minutes on the right. And the times include the walking on the local street network to the nearest bus stop, getting on the bus, potentially transferring, and then taking the bus to a destination and getting off at that destination and walking to the site that contains whatever the opportunity is. So we think that these kind of interactive accessibility analytical tools could be quite helpful in urban planning generally, and we're hoping to make them more robust and performant and broadly available. I think I've already mentioned the compute times are quite fast for the simulations, so I won't say more about that. And I think I'll just close with saying our goal is to have a set of key performance indicators that can be extended by users, because users are going to be in the best position to say what's locally important to them. So we have a variety of these indicators now, but the goal is to make them broadly extensible. And I think the last slide, last little video snippet I have in here is work that we're doing to support collaboration. So it may be around input data, it may be around a scenario that you're trying to create, it may be about the results of a scenario, but having these kinds of markup tools to share a map with someone, share a data view of something, and then be able to let them use markup tools to communicate back to you that there's something that they want to share, whether it's concern about the data that's being used in that location, or the assumptions being made, or the outcome that's being produced. So what we have been doing is creating a threaded conversation platform or component, along with markup tools to be able to facilitate communication through remote use of the platform. And so, you can augment this with, of course, in-person activity and use, but it's particularly helpful when you have to deal with remote work or collaboration across, within and across an organization. So I think at this point, I can summarize that what we're trying to do with the new platform is embed different components and enable them to work together. A 3D physical digital twin, shared data at your fingertips, trusted predictive analytics, land use modeling, transportation analytics, and essentially creating a shared space to shape the future and a collaborative environment to overcome silos. But now I will definitely stop sharing and allow us to have a conversation with what time remains.
Paul, thank you very much. Really, thank you very much for this informative, valuable presentation that it opens the eyes about behind the scene. It's not just about a model or something which is an online. You have demonstrated what's really behind the scene, and this is essential for our junior researcher to know it's not easy just play with a program or software, getting an outcome. No, there's something need to be thought about. There's a lot of work behind the scene in order to get the most accurate, or at least something goes to reality and could present something useful for the user. And I really thank you very much for this point. While our guests might just, or participants might write the questions on the chat part, I might take the privilege to ask the first question, if I may.
Absolutely.
Yes. I can see the model, it's really depending on data, big data. What if some countries don't have that much published data? So how to deal with these issues? Because data, it's I'm not saying it's rare, it's there, but it's difficult to get. In order to train the model, of course, you're saying 30
Right.
years and 10 years. Consistency in getting these data in a way that's useful for a model to be trained, it might be difficult. So is there still a way to get a decent model, but with few amount of data, if I may say?
It is definitely a problem I anticipated we would talk about today. We've worked in a lot of different contexts, some of them predictably data poor, some of them surprisingly data poor, where you wouldn't expect it. Places in Europe or in the United States where you would expect the data to be excellent, but it's surprisingly poor. We've worked in, as I mentioned, South Africa, in the Johannesburg, Pretoria region with Council for Scientific and Industrial Research, or CSIR. And I did actually spend some time on location there, and also in Durban. Obviously witnessed firsthand, and I have done research in informal settlements, even in my graduate education on the Texas-Mexico border, where there's a substantial amount of development of colonias, as they're referred to in that context. They're very informal. They're self-built homes. There's very little infrastructure. The colonias are a staging area for migrants coming across the U.S.-Mexico border. And there are tremendous numbers of issues and challenges. Data, of course, is one of them. But the entire informality aspects of it are also incredibly challenging for models that may have been developed in very different contexts. So in the collaboration we had with South Africa, we first of all had to confront data limitations, data challenges, and we had to make adaptations in the model, not only for that, but also for the informal settlements issues, which we're now starting to take advantage of again in the US-Mexico border, in the El Paso, City of Juarez region. On data, we didn't have, at the time that I worked with CSIR, previously, we didn't have any of this longitudinal calibration technology at hand. So we were estimating models generally cross-sectionally. But the first compromise we made was to use zones as the units of geography instead of going all the way down to representing lots or parcels of land and detailed representation of buildings and things of that sort. So we had to rely to some extent on census data collected at some geographic level. But it was a tremendous amount of data massaging, data imputation, harmonizing data sets. But I would say imputing missing data was a significant element of it. And between the time we were doing that work initially, which was probably 15 years ago, maybe a little longer, and now, I'd say the amount of remotely sensed data and the quality of it, and the quality of machine learning algorithms, segment anything model type applications, has improved dramatically, just dramatically. So my general inclination is that taking inventory for what data is available, understanding what its limitations are, thinking creatively about how to use remotely sensed data, especially longitudinally, and classification of that imagery, and using novel machine learning techniques to improve our ability to do that data imputation work. So it's less driven by assumptions and more driven by techniques that may be black box, but when it comes to data imputation, I'm less concerned about using a black box technique. If it's a neural network that helps me get a well-behaved data set that generally can be ground truthed pretty well, I think it's a good choice in that context. So I think that's an area where there's tremendous potential to improve the applicability of models in places that are data poor, by just taking advantage of many of these emerging techniques that have been developed over the last, say, 10 years and deploying them in creative ways.
That's really interesting. Thank you very much. Actually, we do have 3 questions here in the chat box. One from Mina Nazmi. He's saying, thanks for the exciting lecture. I have a question about socioeconomic models and their impact on the environment. Do we have any applications about them or about it?
Okay, so let me look at the first one. Can we simultaneously apply a hybrid approach that tests architectural and urban design variables? I think this is an interesting question. And as of now, we have really just started to test urban design scale variables. One of my PhD students, actually this was not quite my last PhD student, but one of my last at Berkeley, I'm now emeritus, Jeff Boeing, created some nice tools for taking OpenStreetMap network data and generating different characterizations of the urban design context. They're very easy to use tools. OSMNX is the library. It's a Python library, open source. He developed it while he was my student. And it does some really nice work to be able to process OpenStreetMap data, generate extracts of it, generate urban design metrics with it and the like. I've also collaborated with Andres Sevcuk, who is at MIT, and he's an urban designer by training, but he's also done a lot of really interesting work on network analytics and urban design impacts on everything from walking to retail activity. And so what I'm interested in doing is beginning to harness more of those metrics that we can generate and integrate them into the models so that we can test the effects of urban design scale interventions or urban design patterns on everything from accessibility to rents and prices to attractiveness for location by different types of households and urban development itself. So that's the urban design part. I do find it fascinating, and I think there's a lot of room for improvement using those techniques. I'll note that there has been a fair amount of research on traditional urban design and its impacts, whether there is a price premium for such design patterns. So there is a growing interest in trying to tie analytical to urban design kinds of questions, and I'm quite interested in continuing to do that. Integrating the architectural aspects into this is, I would say, harder. When you're doing metropolitan scale analytics, trying to get data that's of a sufficient quality, first of all, to represent the current built form at a level that's architecturally intelligible and useful is a steep curve. It's a huge challenge. Again, I think there is work. I collaborated with researchers at Purdue University in computer science that do a lot of 3D reconstruction, inverse procedural modeling, and things like that to take perspective aerial images and reconstruct 3D buildings from them, or 3D procedural models that create a facsimile of the building. I think there's a lot of room for further development of those techniques and integration of them. The work that I was showing on generating buildings is, I'd say, very early. We haven't really published it at this point. I want to continue exploring the boundaries of what that can do and how large it can scale. If the performance was good enough to be able to respond to parcel or site geometry and zoning and financial considerations, and the data were good enough to support it, then I think there's an interesting question of whether or not this could scale up to not only transit-oriented development scale, but even to metropolitan city and metropolitan scale. It's an area we're going to continue pressing forward on and seeing what the limits are, what our limits are, and being able to push it forward. Again, collaborations might be quite helpful in that regard. But I do find both the architectural and the urban design aspects to be quite interesting. Let me look at the next question from Mina. Socioeconomic models and its impact on the environment. Do you have any applications about it? Well, if you remember, one of the earliest slides I showed was the urban ecology one. We did a large study, NSF-funded study, trying to quantify essentially the dynamics between urban ecology and urban development. It was quite ambitious. I would say we didn't get maybe as far as we wanted in some ways, but it was quite interesting. I've done work with people working on water demand, where we coupled UrbanSim to a water demand model. And that was a PhD student at University of Washington, and his advisor, Austin Polowitsky, was the student. So we were able to do water demand predictions based on urban development and look at the impacts of urban policies on that. At Berkeley, I collaborated with the Natural Environmental Hazards Research Institute, NERI, and we did some work to study how different policies might impact the potential damage from earthquakes. So we took a particular fault in the San Francisco Bay Area, simulated an earthquake in a particular future year under two different scenarios of urban development with UrbanSim, and we're able to quantify some of the impacts of that. I think that kind of work could easily be extended to deal with recurring flooding events or other kinds of natural hazards, wildfire events. And in fact, we have done a little bit of that with a project for the Environmental Protection Agency in a North Carolina context. So I do think there's a lot of opportunity for both incorporating environmental variables as right-hand side variables that are helping to inform the urban modeling, but also to do planning, environmental planning, for trying to mitigate environmental hazards and risks of various types. So I think that's an excellent question as well. There's been a few more questions added. Intangible factors, this is from Shaima, cultural influence of social dynamics and formal planning, unmeasurable dimensions. It's an excellent question, and it's one that I've recently been having conversations. I was just in an extended trip in Australia and New Zealand, and this question was one that came up in at least two different contexts. It's one of those questions that's almost unanswerable. It's hard. I would say there are some intangibles that you can try to approximate with a proxy representation. There are other intangibles that you can try to capture with I'm a little bit more encouraged about our new calibration technology at being able to do some of this, because we can create a latent variable that, as long as we can construct some instrumentation to approximate it, we can then try to measure a parameter that responds to that metric. And perhaps using our subjective intuition and our cultural knowledge, we can hypothesize metrics that might be good approximations or reasonable approximations and test them and evaluate whether or not they actually help contribute to our understanding of the dynamics. But I think it's always helpful to have a degree of humility about these things and say there are some things that you will just never be able to fully measure, quantify, and so forth. And you have to assume that that's going to be beyond scope of the model. But it doesn't mean we shouldn't try to capture some of these more intangible aspects. So I appreciate that question. There's an IoT related question. This is another question that comes up sometimes. We're generally focusing on longer term modeling at this point, longer term planning questions. And so while I think there is interest in integrating sensors, whether it's energy consumption or traffic movements or some other types of sensors, it hasn't been at the top of our list because that's more around operations. It may be something that we gravitate to later on, especially as we get into things like, say, flooding events happening in real time and how that's affecting traffic movements or evacuations, things such as that. But it hasn't been a major part of our design work so far. We're not trying to do everything, ultimately. We try to do a lot, but not everything.
Yeah.
Yes, there's a couple more.
Yeah. Can I have a question? Because my students
Yes.
were always asking this one. How to get to this field of simulation? I mean, it's just knowing like programming tools like Python or whatever, or learning more about statistical regression models and all of these issues, or how to get into this field, to build a model like the one that you and your team had.
How to get into the process of building the model, or was it about computational performance, or
like postgraduate student would like to be involved in this part, and they like to know the skills, the right skills, in order to start doing this or start to enter this career.
Well, let me take this as the closing question then, since we're running low on time, and I can stay a minute or two longer as well as needed. But you know, I've been working with researchers around the world for my entire academic career, and what I find chronically frustrating is I will visit research labs in places like ETH Zurich, you know, places that are, you know, that have tremendous resources available, TU Berlin, places such as this. And I'll find that their PhD researchers are inheriting code written by the former generation of PhD students. And they want to ask some new question to, you know, develop their dissertation. And they want to contribute that novel piece of research. But what they end up spending 3 years of their dissertation doing, of their doctoral research doing, is rewriting the software that the previous doctoral students wrote, because the previous doctoral students wrote it for their dissertation, which was a little different. They weren't software engineers, so it was learning by doing. Messy code, not well documented, not well engineered. And so the next student that's also not a software engineer has to go through the same hazing process again. And ultimately gets to spend that 10% of the marginal work that they want to do to actually focus on the question in hand. This is why in 2005, I proposed this open platform for urban simulation to try to get research collaboration happening and build on each other's shoulders. For a variety of reasons, and I think part of it is the dynamics of peer review publishing pressure, and maybe a little bit of ego. Individual research and research teams wanted to have their own software. And so this led to just a balkanization of our abilities to move forward. I'm going to take a fresh look at this problem and see if I can, I am now retired from the University of California. I'm emeritus. I don't have active responsibilities there. I'm trying to sustain a small business, which is hard. Yeah. And so I can't volunteer to provide free infrastructure for the world unless we get a Bill Gates grant of a few $1 million or something. That's probably not going to happen. But I would like to think creatively with you and others in your network and others that I've collaborated with in the past about how we might make it a light enough process to enable researchers to access our platform, use what we've already built, extend it, and focus on that 10% that they really want to focus on that's novel, but be able to leverage a collective amount of work that's been done, taking decades of learning and refinement, and be able to build on it instead of having to restart from scratch. I've also taught graduate students at Berkeley, planning students that have no programming experience. I've taught them a little bit of Python programming and a little bit of data science. And it's quite empowering to learn those skills. But when you look at the entire collection of skills to put together a model or a platform, it's software engineering, it's data science, it's geospatial, it's statistics, it's machine learning, it's user interface design, it's so many things. And I think expecting one person to do that in their dissertation is just, it's not realistic. So again, I would be happy to open a door to further conversations about collaboration. I would like to try to find some way to leverage the platform that we've been building to facilitate that kind of collaboration, but I also have limited resources. And so we'll have to find a creative way to address that. So I think with that, maybe it's a good point to close on.
Yeah, thank you very much. I really enjoyed our the presentation, the discussion. It's very insightful. Really, thank you. And I wish that we can build on this to have further collaboration like what you're saying. And I would like to thank all the participants. I would like to thank my colleague, Rhonda and Mariam. Actually, they were handling the questions. So thank you very much. And please, we need to have some sort of another meeting if your time is, of course, available. Thank you very much.
Thank you all very much for participating and for your question. Much appreciated.
Thank you, everyone. Yeah. Thank you, everyone.
Bye-bye.
Bye-bye.